Retaining walls serve the important role of holding back soil and rock, just as dams hold back water. The first video in this series showed that granular materials such as soil and rock generate horizontal pressures that increase linearly with depth. Retaining walls must resist these pressures, and many strategies exist for doing so. In this video, we focus on the popular L-shaped cantilever design. If you were going to use an L-shaped wall to hold back soil and rock, as represented by these marbles, would you point the bottom leg towards the marbles or away from them? Many people would say that the base of the L should face away from the marbles. They probably realize that it is hard to tip the wall over towards the left if the bottom leg points in that direction. In engineering, we call tipping like this overturning. If the bottom leg points the other way around, it is easy to make the wall overturn. So easy, in fact, that I can do it with just a puff of air. It looks like the case is closed. Or is it? Before we declare a final verdict, let's use the model to find out what happens when the bottom leg points to the left, away from the marbles. As we add marbles, we discovered that the horizontal forces they produce create yet another mode of failure, namely sliding of the wall. And this occurs when the marbles reach a depth of 3 centimeters. In the model, we can increase the friction between the retaining wall and the base by placing a rubber mat between them. You will have to do some extra reading if you want to find out how they achieve this end in the real world. As you can see, increasing the friction allows our model wall to support a noticeably greater depth of marbles, but it still eventually fails by overturning, in this case when the depth reaches 8 centimeters. Now let's turn the wall around, so its bottom leg points towards the right, the side where the marbles will be placed. We again use a rubber sheet to prevent sliding, and we add some marbles. As before, the marbles generate a horizontal force that depends on the marble depth. You might be surprised that this wall can hold back 11 centimeters of marbles before it overturns. Can you explain why the wall can resist a greater height of marbles when the bottom leg points towards them? Is there an additional force that comes into play? Recall that granular materials generate both horizontal and vertical pressures. When the bottom leg is oriented away from the marbles, overturning is resisted only by the weight of the wall itself, and so it overturns easily. When the bottom leg points towards the marbles, the vertical pressure from the marbles helps to keep the wall upright. The downward pressure also increases the friction between the bottom of the wall and the ground, thereby reducing the likelihood of sliding. When engineers design L-shaped retaining walls, they imagine them overturning about the point labeled Q. They first calculate how strongly the soil pressure will tend to make the wall rotate about Q. We call this tendency to tip an overturning moment, and we label it MO. Next, they figure out the stabilizing moment, MS, produced by the soil pushing downwards on the horizontal leg of the wall. Lastly, they make sure that the horizontal leg is long enough that the stabilizing moment is at least as large as the overturning moment. Then the retaining wall will be stable.
Now, after understanding what is the question, the first step is to write the given data and draw the sketch accordingly. If you see here, this is the typical sketch of retaining wall. This portion of retaining wall is called as the stem, and this is called as the base. The stem basically retains the earth on this side. So the retained earth is on this side. That is the vertical face. Now let's understand what all data is given in the question. First, they have mentioned about the top width of the stem. So the top width of the stem is given as 300 mm. Then the bottom width of the stem is given as 630 mm. Normally, the top width of stem and bottom width of stem has a ratio of 1:2, but I will recommend you to read the question properly before writing out the data. Next, they have given as the height of the stem. This is the height of the stem. This is given as 5700 mm. Then they have given the depth of the base, and the depth of the base is 630 mm. When the depth of the base is not given, normally the depth of the base is equal to the bottom width of the stem. So remember to assume this when it is not given in the numerical. So this is 630 mm, this is also 630 mm. This is given in the question itself. Also remember, when the height is given of the stem and the depth or thickness of the base is given, the total height when we consider is h1 is the total height of the structure, that is this height. So 5700 plus 630 mm gives you h1, that is the total height, as 6330 mm. Apart from that, they have given us the angle of repose. So this is that angle of repose, and this is given as 30 degrees. They have also mentioned the coefficient of friction mu. So mu is equal to 0.6. This is also given in the question. Then the soil bearing capacity. So as this retaining wall will retain this earth on the soil or the foundation, here the base foundation would be definitely earth. So therefore we need to understand what is the soil bearing capacity. So they have given soil bearing capacity as SBC is nothing but soil bearing capacity is equal to 250 kilonewton per meter cube. The retained earth density is also very important. So density of earth is also given as, if you see the question is 18 kilonewton per meter cube. Density is given in kilonewton per meter cube. And density of concrete, as this retaining wall will be made up of concrete, therefore the density of concrete, let's say density of concrete, we write it here as standard 25 kilonewton per meter cube. So this is the data given. Apart from that, what we need to also understand is the width of base. So this is the width of base. This is 3200 mm. So once we have width of base, we have the width of bottom width of the stem, we can definitely calculate the toe projection. This portion is called as toe projection. And toe projection is given in this question as 900 mm. So we have toe projection as 900 mm, 630 as this given data. So we can definitely calculate this portion which is remaining, that will be 3200 minus 900 minus 630 mm gives us 1670 mm. So this is the geometry of the retaining wall, and this helps us to understand and calculate how much forces it can take and how much moment it will generate. So let's see what are the forces against the stability in the step 2.